Hey everyone, and welcome to the podcast. I'm Brian Beeler. Today we've got a really great conversation, what I hope to be a great conversation about something that's an emerging form factor, and that's the ruler. I'll just leave it at that for now, and we'll get into the nuance of the naming. But the ruler form factor for SSDs, it came out a couple of years ago as an alternative to let mostly hyperscalers have some flexibility in terms of performance and density in these little tiny, barely bigger than an M.2 form factors that are really redefining the way the cloud guys are thinking about hardware and storage and all sorts of other things. We're going to tear into all of that with Jason Adrian, who's part of the OCP group. He's also a hardware engineer at Azure, so has a dual hat and a lot of deep knowledge in this space and has been around for quite some time. So let's bring in Jason. Thanks for coming in.
Hey, good afternoon.
So start with OCP role and then give us the high level of your Azure role so people understand where you're coming from in this conversation.
Sure thing. So I've been the co-chair of the OCP storage project for the past 3-ish years, and I've been involved with OCP since 2013 during my tenure at Facebook. So I've been with OCP for most of the time it's been in existence, both as a contributor and then now as a leader of the group.
Yeah, at OCP, we didn't even know it, but we would have crossed over when you were at Facebook at one of the events out in San Jose, because I remember distinctly Facebook really kind of launching the M.2 form factor into the collective consciousness. So we'll get to that in a second. But even though we haven't spent much time together before, we definitely were approximately nearby at one point. All right, so that's the OCP hat, which is taking a lot of the technology that you're working at in the hyperscale and open sourcing it, right, and pushing it out there.
Exactly. Some of it's hardware, sometimes it's form factors like the E1.S that we're going to talk about. So it's not just hardware contributions where the project started. Now we're evolving into technologies, specifications, things that we can collaborate on, not just with the hyperscale, but trying to bring in the enterprise and OEM companies as well, because we've kind of had this fragmented OEM versus hyperscale for the last, 5-6 years. But we're not as different as we might think. So we're trying to use OCP to bring some of that together. And you'll see some content that'll show that.
Okay. And then your Azure role, you're working on hardware there, which is kind of funny to think about hardware guys in the cloud companies, because we've been kind of taught for a while that the cloud guys care less about hardware than almost anything. So are you just working in some sort of dungeon monkey down there, or what's going on?
It's something like that. So the challenge so what I do is I'm a storage hardware architect for Azure Storage, and sometimes we can find things off the shelf that interest us to build the cloud. I mean, the unit of scale we operate on is hundreds of thousands, millions, whether it's SSDs, hard drives, servers, so quite large scale. And what you'll find is that when something's important enough or different enough, we actually want to go out and build that hardware, either building it internally, building it with a partner. But the key is we have to make sure we're building the right technologies, the right systems, and getting the right performance. Because ultimately, you're right, we are selling a service, and the customers see the service. They don't see the hardware that we're putting in the background. But it's crucial that it's reliable, it's supportable, but most important, scalable. And that's kind of the trick with hyperscale. Customer demand doesn't ebb and flow as simply as an enterprise might. We get incredible spikes. I mean, COVID is a perfect example where not just the volume of what we need to store and compute changing, but it's how people perceive the cloud, the workloads they're putting in the cloud. So, I mean, the last 2 years have been an amazing challenge and exciting opportunity for us to pivot a little bit.
Okay, so you're a storage guy at heart. You've been in the space for a long time, and you recently wrote a ruler manifesto that we'll link to in the description here on LinkedIn that was talking about all these things and the form factors, the direction, and so this goes back to your OCP role of taking a technology that you're adopting at scale in the hyperscale and kind of maybe forcing's too firm a word, but really trying to set the standard for what should be. What's the problem with Ruler right now in terms of the challenges that you're having in getting the industry behind a single shape and size, or maybe a couple shapes and sizes?
That's an excellent question. So let me rewind the clock. It was probably second half of 2019. So
Okay.
we've been consuming the E1.L, the traditional ruler that people are familiar with, this very large device,
Hmm.
that's got tens of terabytes of storage. But it's typically very high capacity, not necessarily the highest performance. Up until then, companies will use M.2s or U.2s for ultra high performance. But again, those are really the 2.5 inch drive is legacy from hard drives. The
Hmm.
M.2, it's great, but it has its own limitations, specifically in thermal and performance. So at the end of 2019, I was looking at the E1.S specs that had started to finalize. Microsoft, Facebook, were very large proponents of that, Intel, Lenovo. So we had a lot of inputs, and there were four form factors in there. So I said, all
Right,
right,
and that's it, just real quick. That's the E1S that you're talking about. So there's the ruler
correct.
long that you just held up that it looks like a little mini yardstick, one of those plastic dudes you'd have in your binder as a kid, and then the E1S, which is basically ruler short, which is
Exactly.
about the same. This is an M.2, about the same length as a 110 M.2, but just wider for a little more NAND package.
Exactly.
Okay.
So there were four options of this E1.S, and we looked at them, but the challenge was they didn't necessarily solve the problem we wanted. So if we wanted high performance and low airflow, the 25 millimeter was the largest one, had a large heatsink on that. That's great, but that doesn't really work well for public cloud because it takes up a lot of space. The
Right.
next
Yeah.
size down was a 9.5 millimeter, what they called the symmetrical case. So it's basically a one slab of aluminum, on each side of the M.2 or E1.S in this case. That gives you some thermal advantages, so definitely better than a raw M.2 would have been, but it doesn't let us really unlock the performance we're looking at. Because when we build something for Azure, we want to make sure that we're not picking a form factor for one generation. We want this to last a few generations. So looking at the Gen 4 SSDs coming out and then PCI Express Gen 5, you're going to be pushing 20 plus watts on these SSDs.
Hmm.
That 9.5 millimeter just didn't cut it. So we basically had an option. I could have said, let's go build a form factor that works for Azure, do stuff in secret. We deployed our data centers as one of the largest flash consumers. Or why don't we open this up, get the OEMs, get the other hyperscalers together and say, how should we do this together? So obviously we picked the second route. I wanted to make sure that we're inclusive. If you look at what we're doing in cloud, we're competing on software features, we're competing on how our systems operate. We're not competing on the piece of aluminum or the thickness of aluminum that goes on an
Sure.
SSD. So we opened it up. We did some thermal studies on our side. We did sweeps from 9.5 millimeters all the way up to 25. I think I showed an image of that in the post I put on LinkedIn, but kind of showed power density versus actual bezel space that you're using in an SSD. So we wanted to find the sweet spot. And that ended up somewhere in that 13 to 15 millimeter range. But instead of just coming out and saying, this is what Azure's doing, you
Hmm.
should follow, we actually brought it to the OCP group. We shared all of our thermal simulations. We had others like Intel and Facebook sharing theirs. And ultimately, we kind of gradually came to this. Maybe it's somewhere in that 13 to 15, similar to what we saw. But we didn't have an exact dimension. So I simply proposed, how about 15 millimeters? So it was kind of a
Well,
nod to
it,
the existing U.2.
yeah, so that's like server width divided by 24 or whatever, plus a little wiggle room on the sides for buttons or something. Yeah.
Exactly. And if you think about I worked at Dell 10 years ago. And if you think about it from a portfolio, you would look at a U.2 platform that they have with 24 SSDs that are
Hmm.
U.2s in the front. Well, imagine a 1U optimized variant, which is where an E1.S is really good for. And if it's the same pitch that has the same ID, the same look, it kind of made a good cohesive story. So instead of us saying, hey, let's go do 14 because that's optimized, I proposed 15 millimeters. Let's split the difference. Let's try to make this something that the OEMs could pick up as well.
Well, yeah, and it's interesting. We can talk about that a little bit too, because, like you said, you're getting 24 drives in a 1U chassis. So a 1U now that we would get with U.2 standard 2.5 inch drive support in it, maybe 10 max on the front, and then if they get kind of funky with some mid plane or some back plane drives, I mean, maybe you can get 20 if you get fancy, but that's about it. And then that's kind of a goofy deployment model. These are all 24 front mount, front accessible, hot swap. I mean, all the kind of enterprise SSD things that we're all used to, right?
Exactly. And that's what the hyperscale wants as well. We may not put the full 24 because we do front access for like our Ethernet ports. But
Right.
having that density, it's important to us because if we went down the U.2 route, as you mentioned, maybe we're putting 8 to 10 if we had to keep space or an Ethernet port. But then if we want a lot of performance, a lot of random IOPS, you're not really getting a lot in a 1U box. And
Hmm.
that's kind of where this E1.S really makes a lot of sense.
Yeah, well, it's interesting. So while we're talking about E1.S, I also want to kind of think about, or I want you to think about and help have the conversation about what the cloud providers are doing and what that might mean for mainstream enterprise at some point. Because we've been seeing these form factors; these aren't new. Been out, like you said, for a couple of years. Supermicro had a couple different ruler chassis options a couple of years back. Lenovo's started to introduce it, but I don't sense that they're, and Dell too. I don't sense that they're really moving a lot of those bays yet. If we look at bay count, 3.5 inch, 2.5 inch ruler, the mix is probably not substantive. Why do you think mainstream business hasn't, enterprise business hasn't moved to ruler? I think there's no incentive, but what's your take on it?
So if we kind of split the EDSF form factors into two, there's the E1.L and the E1.F.
Hmm.
We'll tackle the E1.L first, because I think that's the really easy one. Not a lot of people want to buy an SSD that's 16 or 32 terabytes and putting 10 of them in a system, or 12 of them, or 20 of those in a system, right?
Hmm.
So that's a lot of flash. In the private enterprise space, maybe there's some customers that want that, but is it really a big enough market? Probably not. In the
Okay.
hyperscale space, we need this. I mean, we're selling petabytes of flash, so we need this density. So I think that's where you see this E1.L being very hyperscale centric, and maybe in the future in some of these edge locations, you might see this as an interesting form factor. But if we look at what the OEM space has today, U.2 is everywhere. Your 1U systems, 2U systems, 4U systems. There has to be a lot of incentive to move to a different form factor, right? Because then you need adapters if you want to move them around. I mean, if you're an enterprise consumer and you have a mix of boxes, and let's say you have 2 terabyte or 4 terabyte SSDs,
Hmm.
you don't want to stock an E1.S for these systems, a U.2 for those systems. It's just not a good sourcing strategy. So what I think is going to start shifting this is that as clouds start bringing a lot of volume on this E1.S form factor, from the 1 to 8 terabytes today, it'll go to 16 plus in the future. Once that's prevalent, I think the incentive is going to be there to start adopting it on the OEM platforms, especially as this hybrid cloud concept comes to play, where you may start having similar performance mechanisms, similar hardware designs that you would put in the cloud and on premises. And
Hmm.
now you actually can start saying, hey, these actually match. So I think the slot compatibility gets a little bit better. But then the other thing that's also going to help this is the cloud SSD specification that was contributed to OCP. I think that was earlier this year, version 1, and there's going to be a version 2 coming up shortly. And while it started as Microsoft and Facebook, now Dell, HP, and others are contributing to this. So now
Yeah.
you see these E1.S systems and E3 in the future no longer being driven by the hyperscalers. Now it's a whole community, right? As we talked about earlier, we don't really want to fragment the market. We really want the market to be fairly unified. And I think you're going to see that happen in the next year or so. I think 2022 is going to be a good year. We're going to see some of these new form factors and you see systems coming out that really make sense that will start incentivizing people to say, hey, maybe we should look past U.2. There are some other options out there. They're unique for flash. They're not a hard drive replacement form factor.
Well, yeah, you're right. I mean, there's certainly a lot of SSD options too. We're working with SK Hynix on a ruler project with Viking. Viking's got, of all the mainstream available servers out there right now, you referenced the Viking server in your paper, but AMD board, 24 slots across the front. Again, 1U, really neat engineering. We're looking to get our hands on one of those bad boys right now. And you talked about engineering and the 15 mil, how that's important. And it's actually probably not a trivial thing. It probably is actually really important in that their system design already exists now for the 2.5 inch SSDs and a 2U, and then they've got the board for the 1U and the cooling setup there. But if all they have to do is work on the engineering for that front little bit of the storage plane. The rest of it they already have, so it's not as if they have to from whole cloth create something brand new. Though I suppose they might need to deliver a little more power. But yeah, really looking forward to seeing that Viking box come in and get those Hynix drives. Should be pretty fun to start playing with that technology.
So the Viking box is very interesting. That's kind of what I had in mind with the 15 millimeter. I think it highlights, you're asking, how do we see the transition moving away from U.2? So let's take the Viking as an example, where you have SSDs plugging directly into a compute module. That's the intent, right? So when you start looking at PCI Express Gen 5 SSDs, that is, I think, going to force the E1.S transition in a 1U box. Because if you want U.2s, you're not going to be able to put those natively. You're going to have a backplane. So all of the 1U boxes today have backplanes in it. You don't really want that at PCI Express Gen 5. You're going to have cable assemblies like you do today. It just gets messy. So if you kind of fast forward a year or two, now with the E1.S's, you've got these right angle connectors. I have an example of it here. I mean, this is directly on the board. Let's see if I can get it to actually go in focus.
And there you go.
There we go. So that can go directly on the motherboard. So you have these connectors directly on the motherboard, and you can go to a PCI Express Gen 5 SSD with no redrivers or retimers, no backplanes, no cables. That's where we want to get to. I mean, that's not unique to hyperscale. People don't want cables. They don't want complex systems. You want it native. And that's kind of how that Viking is maybe a transitional product where, it's got some large backplane connectors. It shows you where the future is going to go.
Well, I mean, they're on the front end of that when you look at what they do. Their business is to create those systems for other vendors and other partners, and so they've got to be there. So like you said, there's this Gen 4, the drives we're going to be getting in Gen 4, so we should see some nice performance out of that box, and as you say, as a transition to Gen 5. So you think Gen 5 is the inflection point that changes the game for where E1S could see more broad adoption?
I think Gen 5 is going to force E1 and E3. So for high...
We're going to start in on E3 already?
Well, E3 will eventually be there, right? I mean, that's kind of the successor to U.2. I mean, it's been limping along, but U.2, U.3 has been fairly healthy. And really, Gen 5 is the only thing that's going to force E3 adoption. So I really think Gen 5 is the inflection point. It's going to force all these new form factors. It's going to be across the data center, the OEM, and I'm honestly hopeful we'll see this in the client space, in the workstations and high-end desktops. I mean, there's a lot of opportunity for SSDs that have the thermal management built in. And I'm watching, the Chia miners running these SSDs, seeing them throttle, and it's like, well, yeah, you're running a bare SSD. You're not cooling the controller. You're not cooling the NAND. All these aftermarket heat sinks that are fitting in there, but that's really not the right path. You really want to just build it all in to a module and plug it in.
Well, it's funny. I got out some of our M.2 stuff. We've got stuff like this gigabyte card that holds 4 drives on it, and that's what some like the creative pros that are running rendering jobs or using intensive software with intensive workloads or AI in your local machine, if you're a data scientist or whatever. They're having to go to some creative concepts like this, the Honey Badger from Liquid or others, to be able to get the performance they need out of the storage. And it's not, as we've seen, and I'm sure it's not always reliable. The quality difference between this gigabyte card is actually pretty good, but we've seen some stuff that was just hot trash that looked like on paper that it would be great. And you plug it in, there's all sorts of compatibility problems, drive overheating if they don't have active cooling on it. And then you've got some of them that are so long, you need a big liter PC case for. So yeah, I could definitely see giving these guys a way to have access to more faster storage. Like why not? So that's the client space on workstation. Can it ever work in a notebook? I suppose maybe not with the thin and light requirements, but maybe a larger workstation?
For the workstations and desktops, I think that's where you're going to see it. For a laptop and really thin machines, they're just going to solder it down or do their own custom form factor. Or, I mean, the E1.S spec has a non-cased version, but it is, right. And that's not something you want to put in a dense laptop. So I think you're going to see either customized form factors, or maybe they'll adopt a modified version of an E1.S. It'll be interesting to see where that goes. I mean, modularity is mostly gone in laptops these days. Everything is about thin and light, fitting the rest of it with batteries. So the SSD is an afterthought.
Yeah, making the build simple, and most people aren't in that class of product aren't running upgrades and that sort of thing anymore. Anyway, so do you think then, as E1S gains popularity, does this M.2 connector eventually go away? Is that done?
That's a great question. So I think for the enterprise and OEM and server market, absolutely. I think you're going to see the M.2 connector disappear in the next year or two from new products.
Okay.
The client space is a tougher one, though, right? The client space has the ability to put these down on a motherboard. You can do the same thing with an E1.S, but with heat sinks, then you're going to start blocking slots. So it'll be interesting to see where that market goes. I mean, with U.2s, you're already cabling, which you can do the same thing with E1.S. M.2s were the first opportunity for a motherboard to put them directly on the motherboard. So there's nothing separate. That's going to be a tough one. I think M.2 will probably survive a couple more years there. I'm hopeful that maybe the was it the 5.9 millimeter E1.S, where it's basically a small heat spreader on both sides. Maybe that'll take over in the client space, but it is a bigger module, so it'll be interesting to see how these fit in.
Yeah, I mean, I was thinking before, and I forgot to mention it, but when you were talking about taking complexity out of the system design with the Gen 5 SSDs, it's actually interesting because you say you just sort of a throwaway comment, you get rid of cables. Last week, we had an NVMe cable fail to the front of the box in one of our servers, and Kevin's over there working like, I've got 8 SSDs and only 7 are showing up. Like, what the, why is this happening to me? And he tried, he took it out, reseated it, switched it, go through all the things. And we never think it's going to be the cable because they're so reliable. But sometimes it's the cable. And so he harvested one from another system or inside, and that was it. And it was the 8-cent cable that took the data store offline. It's amazing.
And that's what we're fighting in hyperscale, right? So if you look at the systems we're building, we try to avoid cables wherever possible for exactly that. So if
That's
you're
because you guys are so cheap. You're just trying to save money.
frugal is the word. Efficient. Sorry, efficient's probably a better.
Yeah, there you go.
It's not necessarily about cost though for us. I mean, obviously cost is important, but it's about serviceability. You mentioned trying to track down a problem. We don't have time for that. We build our systems to be reliable and easily diagnosable. If something goes wrong, the way it should work is we have an automated system. It looks at the log, says it's this product. It's an SSD, it's the CPU, it's the DIMM. We send a technician out, replace the part. Hopefully it's the target's probably like 2 to 5 minutes maximum. And then they're
Really?
done.
Wow.
That's what we want. If we have to have technicians digging in there, moving cables, as soon as you move a cable, whether that's the one you want to touch or not, you're going to break them at some point. If you're going to ship millions of servers, they go thousands of miles on trucks. Things can get loose. They bounce around. Cables are just not a good thing at scale. Small scale, tens of servers, it's manageable. At our scale,
Sure.
we can't afford to have that.
Well, when does it get to the point? I mean, there was always that conversation that at the hyperscale, when things just aren't working, they just rip the server out, throw it in the shredder, and put a new one in. Is that a reality in your world?
It's not a reality in our world. So our goal is that we replace just the component that fails. So in an event where we can't diagnose what goes wrong, we will pull the system, we'll bring it back, and we'll test it on the bench. If we can't figure it out, we'll RMA it to our partners. We try not to shred anything. I mean, we're doing our best. We going carbon neutral, carbon negative, across all the hyperscalers. Microsoft's a big proponent of that. And we do everything possible not to destroy hardware. We try to reuse it where possible. Ultimately, if something is bad, it will get RMA'd. If it can't be repaired, then yeah, it'll probably get recycled.
So as your model's changing with SSDs to be faster and faster and faster, and then of course capacity for the capacity tier, are you learning? What are you learning new that's interesting? Are you seeing challenges in environment or in endurance? You talked about heat a little bit. As the drives are getting faster and higher capacity, are those two growths creating new challenges for you?
Absolutely. So you mentioned two pieces, and those are two very interesting challenges. One is performance, and one is capacity. So let's start with the capacity because that's the easy one. If you look at the system we contributed to OCP, I don't know, it's probably 2019, 2020. I forget the code name, but it was basically 16 E1.L SSDs. You can put, two servers, so each could have 8, or all of them could be connected to 16. Well, if you're putting a 16 terabyte SSD in there and you have 16 of them, now you have hundreds of terabytes of SSDs. That's a lot of capacity. So you might think you understand your workloads, right? So we may characterize our SSD workloads today, call it X number of megabytes a second.
Hmm.
Well, workloads can change, and we have that much capacity in a single system. A customer or a group of customers, the whole workload getting to 2 or 3 times the throughput. Now you're saturating your NICs. You're going from 40 to 50 to 100 to 400 gigabyte NICs. I mean, gigabit NICs. You're moving, and you have to figure out what's the right design standpoint. So that capacity is driving a lot of that. Driving what is the right workload. Then you mentioned endurance. I mean, the performance and endurance go hand in hand. If
Hmm.
you're expecting some number of drive writes, per day, and then all of a sudden you've deployed this, and a year later your workloads get substantially hotter, the market changes. Now you have to handle that. What happens at end of life? Do you start wearing your SSDs out earlier? If you have 16 of these 16 terabyte SSDs or 16 32 terabyte SSDs in a box, if they start failing, that's a lot of capacity to replicate elsewhere. So then you have network storms.
That's
It's just
yeah,
a
yeah.
lot of work.
Well, like in a traditional storage array, you worry about like RAID rebuild time or whatever. I mean, if you've got an NAS, anyone that has a Synology or QNAP at home in their basement, you throw another, even a modest 8 or 10 terabyte hard drive in there and have to rebuild that RAID. It takes forever, forever. Like when we do the reviews on the NASs, we'll throw the hard drives in and then go create the volume and leave for the night and let it do its thing and chunk along. Understanding those are hard drives, but the reality is still the same for SSDs. Time is, in your case, money, right? So if that system's offline or replicating or doing other stuff that's not, creating revenue, that's suboptimal.
It definitely is, but we do have some secret sauce to be fair in hyperscale. So we're not taking hours or days. We do some interesting things to
Sure.
speed that up. But you're right on though. Anytime we're doing replication or rebuilds, that's traffic across our network, traffic to other
Hmm.
SSDs. It could impact the latency. So I mean, we have a lot of things that we have to keep in mind. So that's kind of the capacity side of it for us.
Well, stay on capacity then. What's your take on QLC? Are you seeing decent utility and adoption there? Or is it too early for mainstream? What do you think?
I think QLC is a good fit now. I think QLC took a
Okay.
little bit of work, both for us and others in the industry to work with and adopt. You do have to pay attention to the endurance cycles, but if you look at how the market is moving, you have some that are just about performance. How much performance can I get out of SSDs? That's really high workload. But then you have a very large segment of the market that can be serviced well by things like QLC, ZNS, which is going to help us manage some of that. Because if you can promise low latency, but maybe not the high bandwidth that people expect on like the HPC side, but if you can just give people predictable low latency, that's a great fit for QLC. So I think you're going to see a lot more QLC shipping, both in the enterprise and the hyperscale market. Not everybody needs gigabytes a second out of an SSD or hundreds of thousands of random IOPS. Not a lot of people actually use it. They're great for marketing numbers, but realistically, what people need consistent low latency access, and the prices are coming down quite a bit. So it's actually within reach, I think, of a lot of customers and a lot of companies.
Well, you have at Zero though. You've got the ability to customize your code to be gentle on the QLC and give them sequential writes and read a lot. And so not everyone's got that ability. I think that's some of the hesitation when you take them into a standard mixed workload scenario where they're really not quite ideal for that to just drop in replace for TLC drives. You did say one other thing though in the middle there, ZNS, zone namespaces. You want to do a quick hit on that and just as a primer for people? I don't know that that's widely understood yet in the enterprise.
Sure. So ZNS allows us to start grouping either dies or specific areas of the SSD and allows us to address workloads to specific pieces of it. And there's some great articles out there. I don't want to go into the depth of that. On
Yeah.
LinkedIn from others, Western Digital has been a huge proponent there. They have a lot of information out there. But what that's going to allow us to do is kind of give us a little more control over the firmware transaction layer. So instead of just blindly writing to an SSD and letting it figure out where the data goes, now we can start specifying that we're going to do append only. So it used to be called append only streams, where it's like SMR for SSDs. you consistently write into a specific spot because we know how our customers actually address data. Because you mentioned earlier, we kind of control that. We're kind of sitting in the middle there. A
Right.
customer doesn't directly write. So if you have the ability to start combining writes together and then putting them in the different zones where you're not going to be deleting them all the time and having to do erase blocks, it allows us a little more control there. So what the real benefit of ZNS is going to give us is the ability to place data correctly and reduce the write amplification of kind of recollecting all the blocks as there's gaps in our data, we get deletions. So it's going to help quite a bit.
Does it get you a lower cost controller then potentially on the SSD since the drive's doing less work? Is there power savings? Are there any other peripheral benefits there?
There definitely are. You can slim down what the controller needs to do. You need less
Right.
memory in the controller. How that translates to end price, that's to be determined. But from a bill of materials of an SSD, yeah, you can simplify it quite a bit. Again, the flash still dominates. So if you're talking dollars out of an SSD, that may cost a couple grand. If it's
Right.
a 16, 32, 64 terabyte SSD, it is small in the scheme of things, but it is something. That's something that we're interested in taking advantage of, right? You mentioned time is money, efficiency is money in the cloud. If we can get an extra 1%, 0.1%, we basically no longer have to over provision SSDs. Now we can natively use the full capacity as we start going through the endurance cycles. Then we can figure out how to use the rest of the SSD or maybe pull some stuff off there.
Okay, well that makes sense. So you were talking about the capacity side, kind of what you had been learning there. When you think about performance, what's happening on that side in terms of how you're re-educating yourself on the daily basis?
Okay, so if we switch back over to kind of the performance side of the world, I mean, we've been using M.2s. We've used them in cards like this, the Ava card, to try to cool them. Uh, Ultimately, we kind of start off with bare M.2s, putting them in our systems. If you look at the Olympus specification of blades out there, you'll see that they have some risers with M.2s. That works okay if you're doing boot and you're doing low performance SSDs. Even in Gen 3, though, you can start heating these SSDs up quite a bit. We don't want to increase our workload, our airflow too much. Again,
Mhm.
airflow is money, airflow is power. So that's where you see those Ava cards come into play to help cool them off. As we look in Gen 4 and Gen 5, you're going from these 8-watt SSDs to 15 to 20-watt SSDs. Well, now that changes the game a little bit. We can't just stack them all up really closely, vertical on a motherboard with no heat sinks. They absolutely have to have thermal control. These Ava cards, we outgrew those pretty quickly. You can put 4 in a slot, but in a one-use server, if we're occupying one with a NIC, that leaves you 2 slots. So 8
Yeah,
SSDs
not a lot of room
on the
left.
motherboard. That's not a lot. If we need to hit, let's say a customer, or a use case says, I need 2 million, 32K random IOPS. Okay, that's a lot of M.2s. So now you're saying, all right, now we got these E1.S modules, they got these heat sinks on them. Well, now we want to front load them in there. We can put a lot of them in there. We don't have to worry about throttling. And in Gen 4 and Gen 5, we want to take advantage of that. I mean, these things are going to hit 10 plus gigabytes a second per SSD. I mean, it's really hard to fathom. I mean, that's a lot of performance. Can you consume it? Only the use case will determine that, right?
Sure.
Not many systems can really process data quickly enough to hit, call it 10 or 20 of these SSDs at, gigabytes a second. But look at where the CPU vendors have gone. I mean, AMD's EPYC is just, a fantastic CPU. 128 lanes, you've got 64 cores on it. You can natively connect a ton of E1.S and actually process data pretty quickly. Put 2 of those in a box, now you've got a ton of flash performance. You got a ton of, compute in the back to do something with it. You actually can consume these Gen 4 and Gen 5 devices. So as long as you can cool it, that's the 15 millimeter E1.S we drove. Now we can actually use it. You got a CPU that can actually handle it. You've got the SSDs that will keep up with the workloads demanded of them. And now you have 400 gigabit networking that's becoming fairly ubiquitous now. You can actually get data in and out of the box. So it's going to change what we used to do. I mean, Gen 3 M.2s really can't hold a candle to what these new SSDs are doing.
Okay. All right, so we had a minor technical difficulty. I had to switch earbuds. The other one died. Okay, but you were talking about what you learned on E1.S. anything else stand out?
It definitely does. So we talked about the performance and thermals a second ago and different architectures, but there's one other big one, that's very interesting. When we were using M.2s that are hidden inside the box, you can't do online serviceability. You take down a node if an SSD goes bad. And that's not something we want to do in the hyperscale. We want to do everything online where possible. M.2 really isn't the best form factor for that. U.2 is great, but as we talked about earlier, it takes up a lot of space. It's just not a form factor that we went after. With E1.S, though, we now have that front accessible form factor that we need. You're seeing the CPU vendors supporting NVMe hot plug, I should say PCI Express hot plug. So now you have devices that can be hot serviced. You're not going to blue screen your machine if you pull out or surprise insert an SSD. So that really changes the paradigm of when you take a blade offline. You've mentioned it a couple times that time is money. That's absolutely right. Uptime of our systems is money.
Sure.
We don't take down a system. We can swap out an SSD. That's fantastic for us. And E1.S is really unlocking that in our next generation systems.
Yeah, you don't want to lose those Minecraft player files. That's very important data. So we've talked a lot about traditional servers, and you mentioned Blade, and I don't know if that's just what you call any node, but does the change to these ruler form factors change the way you guys want to consume hardware in the cloud?
I'm not sure if it necessarily changes the way we consume hardware, but it gives us more design flexibility than we had in the beginning. We've had E1.L boxes, for some number of years now, and we've got some great systems on that. But for the E1.S, it's actually given us a few new things where some of our boot or caching drives were kind of tucked in, like I mentioned. They're not anymore. Now we can bring those to the front. So that does open up the ability to kind of build systems that are a little bit different, get everything into the front. If you kind of look at the tenets of all of hyperscale, it's keep everything in the cold aisle, make everything hot serviceable, don't have people take out systems. Obviously, if your CPUs are failing, your DIMMs are failing today, those are typically coupled with your systems themselves. So you're going to pull out a system to service those. But your SSDs shouldn't be. If you've looked at SAS hard drives, SAS SSDs have always been hot pluggable. We've kind of gone back a little bit for NVMe SSDs. I think this puts us back on par with where we need to be. So we're going to build systems a little bit differently. You're going to see disaggregated storage boxes pretty much across the board, I think, in the next couple of years. That's not necessarily tied to the form factor, but it certainly gives us the ability to make some very dense systems, maybe mix and match of E1.L boxes, E1.S boxes. When E3 gets out there, that might displace, a little bit of each of those other markets.
Well, it'll be interesting, though, for even like the traditional Blade guys. We've got a chassis in the lab right now that came in from Supermicro, and it's got these little half blades. You can fit, 20 of them or something in their chassis, but they only have 3 drive slots. So they've got a SATA boot drive and then twin NVMe, which is probably fine for the workloads that type of system is used for. But in that same real estate now, you could get like 6 drives or maybe 7 or 8 if they got creative in this tiny little half blade. It just dramatically changes the dynamics, the smaller the footprint of the compute in terms of what you could do there from a storage perspective.
That's actually an excellent example. If you look at, let's say, 2 U.2s, you can replace those with 4 E1.Ss. And realistically, they're the same controllers. Yeah, you might have a little less NAND behind them, but you're going to get more performance out of 4 E1.Ss than 2 U.2s. So in the example you said, you're going to get higher performance blades, better kind of fault isolation. You don't have to put, let's say, 2 large devices in there. If you wanted to mirror that, that's nice, but if you had 4, maybe you can stripe across it. You're going to get more options in there.
So we talked about how the drives on the performance side unlock networking challenges and causing you to go from 25, 50 was pretty good a year or 2 ago, or maybe 2 years ago. Now everything's got to be in the hundreds of gigabits per second to let the data come in and out. But the bigger challenge, or one of the bigger challenges I think that we see even on just a single node test, is that with the latest Gen 3 Epics or Xeons, we can pretty much peg those with 4 or 5 SSDs of today's Gen 4 standard without a whole lot of effort. So some workloads are going to be CPU constrained. So as you think about, you're a hardware guy, Do you put more CPUs in these boxes, or how do you think about that from a maximizing the workload per rack queue?
That's an interesting question. I think there are probably several different answers depending on use case, right? So in a very generic use case, yeah, you're going to need more compute depending on the workload. So I think you mentioned 4 SSDs, maybe you're pegging the CPUs. So yeah, the core counts of future CPUs are going up. So that will give you more slots. But I think depending on the workloads, you're going to see more hardware accelerators. You're going to see a lot of the computational storage. There's several different vendors out there that can actually do some processing on the SSD. So maybe you're not going to be doing as much on the CPU. And I think architectures might solve a little bit of this as well. So in the example you gave, maybe you have some nodes that are really pegging the CPU doing a lot of data processing. When you start thinking about a disaggregated architecture, you see NVMe over fabrics. I mean, there are a lot of other ways to connect flash that maybe you distribute those workloads over multiple nodes. So I think architecture is another potential answer. So whether it's computational storage where you have intelligence on the SSD, or you have companion cards in the box, whether it's an FPGA or these very high core count style devices you can plug in there to do some of that computation. That's another one. But if you're really just core bound in a general workload, I don't see that changing other than following the CPU roadmaps.
Yeah. It's just an interesting challenge because we see all these, you talked about some of the high level, side of the box benchmark that's normally on these enterprise drives, and they'll say 7,000, 10,000 megabytes per second, whatever the number is. That's one at peak workloads. But when you put, like I said, just 4 or 5, when we do some of our SQL tests, we can just nail that CPU, and there's nowhere else to go with it. Like, you can put more drives in there, more capacity, but you can't get any more working set doing anything, and that's an interesting challenge. So you talked before about E3, and I'm not sure how deep we want to go into this, but if you believe in rulers so much, why do you think we need another rectangle form factor in the close to U.2 size? What's the upside?
So that's complicated. So if you are a hyperscaler like Microsoft, E3 may not really bias all that much. We've got E1.Ls for capacity, E1.S for performance. We're happy. I think E3 is going to be more interesting for the OEMs. They've got a 2U box today. What is the roadmap to getting more performance in a 2U box? Do you simply put E1.Ss in one of the U's and use the other U's for I/O? That's certainly the path I think I would want to go. But again, the OEMs are going to have to make that call. And I think they're going to have to make that choice of, do we make something that looks the same so you get very high capacity? And that's what E3 really does, right? E3 is going to give you, twice the width of an E1.S, so you're going to get double the capacity. Do you really need that? That's to be determined. You didn't see the OEMs going for the E1.Ls because it makes the box really long, right? You've got a dual socket system, you got fans in the box. If you're putting these E1.Ls in front, it's really making those systems really deep. Great for us in hyperscale. We love it. Not so good for, the OEMs. They have to sell into telco markets. Maybe you have a 20 or 24-inch server depth requirement. So I think that's where E3 is going to try to replace kind of the U.2. That either the OEMs will say, look, let's follow hyperscale, 8, 16 terabytes and a U1.S is enough. And I generally think you're going to see some of those systems come out. But I think there may be use cases where someone says, I have a 2-socket, 2U system, got a lot of I/O coming out the back. I need a couple hundred terabytes of flash. You're probably not going to get that in E1.S in the front unless you do backplanes. And if you're doing backplanes, maybe it's worth it going E3. So I would certainly like to see the market stick to the E1.L, E1.S. I really do think that gives you good options. But I think the OEM, there's a lot of tradition, a lot of what looks the same, keeping customers happy. New is scary sometimes. And I'm assuming customers, they see these small devices, oh, it only goes to 8 terabytes. Well, not many people are buying bigger than 8 terabytes today. By the time you need to consume it, there'll be 16 terabytes. So I think that's just a little bit of FUD that people are, what if? I need more capacity, I need more of this. So we'll see. Let's see, what is it, 2021. By 2025, let's see if E3 is really gone big or not, or if people have said E1.S is good enough.
That's a long way to go. Well, without support from the hyperscalers, can a form factor like that be successful? Is there enough volume out there in the rest of the world, minus the big cloud guys?
I think there is. I mean, if we really dissect what's inside of an SSD, most of the R&D is in the controller and the NAND.
Hmm.
For them to relay out a U.3 versus an E1.S, okay, there's some work, but I mean, Dell, HP, Lenovo, they sell so much. I think they could keep a form factor alive. So if they want to do it, kudos to them. That's fantastic. I think a better approach, and one thing we actually did talk about, so kind of rewinding back to OCP, we tried to get the E3 form factor to adopt the length of E1.S because the
Mm.
connector is already the same. So one of the ways you can sort of split the difference is you can say you build an E1. I got one of these boards. So you take a raw E1.S PCB that's like this. You put it in a U.2 or an E3 form factor, just an empty shell. You can use the same 8 terabyte SSDs, and it plugs into a 2U optimized form factor. No difference, right? That's a good way to do it. And then if you really need those high capacities where you want all that space, then that's where the E3 is going to fill in. And I think the E3, the other thing that may kind of keep E3 alive, if you're looking at these computational storage devices, if you want to put in very smart accelerators, you're not going to put big FPGAs or very power hungry ASICs in E1.S, right?
Hmm.
That form factor is 20, 25 watts, and it's narrow. E3 gives you the ability to say, well, I can have an SSD, or I could have an accelerator or a computational storage device. So I think that's where you're going to see, from a modularity perspective, that E3 does have some good concepts there. And I think the OEMs will embrace it because then they can kind of mix and match in the same system, and it gives them all the options.
So speaking of options, you highlighted a couple there. Computational storage is interesting. There's a lot of guys running around out there with drives that do different things. We just took a look at one computational that was targeted to compression, and so something that's been around for a long time. But the switch on this one's got a little extra controller in there to help with compression and dedupe, I think, too, if I remember, and get you a little more footprint out of that drive at the hardware level, which is interesting. Because in most cases we're limited to software to do that now. So you've got to do that either with your application or have an inline compression engine, whatever. But that puts additional weight on the CPU, and as we were just talking, the CPUs are already getting hammered enough as it is. So the idea of computational makes sense. You talked about some fabric stuff. You talked, not specifically, but Xilinx and NVIDIA Mellanox both have these smart NICs, whether it's Bluefield from NVIDIA or the Xilinx offering. So there's lots of stuff out there. A couple startups running around with DPU storage. How real is that from the adoption standpoint? And as a hardware guy, is that something that interests you, or is it too far afield or too early for mainstream adoption for even the hyperscalers?
So I think you'll see that all the hyperscalers, all the OEMs, we're all interested in these offloads.
Sure.
We want to get general purpose cores kind of out of our data path. If you can accelerate that somehow, whether it's in the device, accelerators paired with the CPUs, that's definitely better for us, especially because in the hyperscale, we have predictable workloads. We know what we're doing over the network. We know what we're doing down the devices. We can find ways to accelerate things in hardware. So, and we're certainly working with many vendors out in the industry to help shape, the products they're bringing to market. But I think you'll see a lot more prevalence of that in the next couple of years.
Okay. So OCP is coming up. It's scheduled to be in person in San Jose. I'm a bit suspicious that it'll go off that way, but we shall see. What are you excited about this fall coming into that show, and what are you enthusiastic about?
All right, I'll give a plug for what we've been doing in the storage work group, kind of what's been completed and what's coming up
Yeah.
next, because I actually think it's pretty exciting. In terms of what we've done over the last year that we're going to talk about at the summit this year, we have the E1.S 15 millimeter. When we talked about this in the summit, was it 2020? It was back in, was it May? I forget when we did the digital
Mhm.
version. We talked about 15 millimeter. We'd all standardized it. We got it put in to the TA 1006 spec, if we can get a number right, to get that 15 millimeter in there. Now we're coming back 18 months later, and we have 8 different vendors building 15 millimeter E1.S. That's exciting. I mean, what is that, 16-ish months to go from, yes, we're standardized on a width. Now every SSD vendor out there is building it. That's exciting. I mean, being in the industry for a while, form factors take a while, especially from an adoption standpoint.
Well,
Yeah.
yeah, but the business guy in me says, I mean, you got the money, so what the hell? Like, of course they're going to go build what you want, because when you show up at Best Buy with your shopping cart to buy flash, you're filling that thing to the top, metaphorically speaking. So, yeah, I mean, they'll build what you want if you've got the money to buy it, right?
Yes, you can certainly be the gorilla in the room and hey, let's go build this. But I think what we did through OCP is kind of getting all the voices to come together, that you didn't have this, one or two large companies kind of putting pressure. I think it was a good collaboration of hyperscalers, OEMs, and consumers, all the flash vendors. So I think it's really great to highlight, the Viking boxes out there. I mean, Supermicro was certainly early. They did the 9.5 at the time. Now they're making 15 millimeter latches, so you can put the SSDs in there. So that's exciting. We're going to talk about hard drives, which some people forget about, but the
What?
the bulk of storage is still in hard drives. People sometimes forget about that. So through the work group, we built an acoustic surrogate specification that
Hmm.
basically says, here's how you put some microphones into a slot, and you can actually characterize the storage slot. The reason that's important is when you get to these high capacity hard drives, the noise of the fans, the noise within the data center, vibrations, everyone's familiar with rotational vibration, not as much about acoustic vibration. Back when I was at Facebook, I designed Bryce Canyon, and we actually hit this firsthand. I mean, we had issues with, certain vendors, in the 10 terabyte range that had this issue where you put them in the back row and the high frequency noise from the fans was actually causing quite substantial performance degradation. So we
Hmm.
tweaked our box, we partnered with the vendors to solve that. But it was kind of a trial by error, and we presented to that effect in the OCP work groups at the time. Here's what we did, here's how we fixed it. This acoustic surrogate comes in now and says, look, everyone doesn't have to build their own, setup. You don't have to figure this out on your own. Here's the surrogate. You put this into the slot. It's standardized. Now, Western Digital, Seagate, Toshiba, they can all look at the output from that and say, yeah, our drive will or will not perform well in your box, or here are the frequencies that are problematic for us. So I think that's really exciting that you see a lot of hyperscalers kind of and the drive vendors partnering to drive that standard. That really wasn't there 4 or 5 years ago when I was tackling this challenge. We kind of had to figure it out on our own. So I think that's a really cool thing to see.
That is pretty cool. Next, you'll tell me you want to put NVMe on hard drives.
Oh, all right, spoiled it, spoiled it. But yes, we actually do want to put NVMe on hard drives. So the fun part about that one is, a couple years ago when I was suggesting that, I think people would look at me and wondering why I was in the room, like what was wrong with me, was I
I
drunk the
still
whole
think there's
time?
something wrong with you.
And that's probably true. I can't argue that one. But here's how it becomes interesting. If we've looked at where hard drives have been, we've had SAS and SATA for what, coming up on 2 decades now.
Hmm.
They've served us really well. What has changed, and we've kind of talked about a little bit earlier today, is that things are a little bit different. We're no longer building these enterprise systems in hyperscale that we're daisy chaining hundreds of drives. We're building smaller systems. They're all typically contained in a box. You don't see us daisy chaining out multiple enclosures. And now, if we want to get CPUs out of the way, we want to have these computational storage type devices, or we want other devices to be able to talk to the drives. Maybe we don't want to go through that host CPU. And that's kind of where you get a hard drive on a PCI Express bus, use the NVMe protocol. Now anyone that can get access to the PCI Express bus can talk to it. You mentioned smart NICs earlier. I
Hmm.
mentioned kind of accelerators to CPUs. I mean, there are a lot of things that can be opened up when you put a hard drive on a PCI bus to behind NVMe. So it's certainly, we're not doing it for performance. Hard drives, are not magically going to get faster in the next couple decades. We're increasing at dual quad actuator. You'll see that, but again, the bus is always going to be faster. This is really about getting the SCSI controller out of the way. We don't need a SCSI controller anymore. SCSI was really meant for all the hot plug events, cable insertions. We don't necessarily need that, but we do need cost efficiency. So we can't go build this high power device like a dual port SAS drive. We kind of want to slim that down for power, want to slim that down for cost. And that's kind of what we've been doing over the past year in the OCP work group. And at the summit, we're going to talk a lot more about that. We'll have a draft specification, and then if you stick around, we actually might have some interesting surprises that we'll show at the summit that might
Ooh.
surprise people. So.
All right. Well, there you go. There's the hook to show up or tune in or however that goes down. Why do you think, I know you wanted specific form factors for your needs at the hyperscale, but why didn't the 3.5-inch bay ever take off as a house for SSDs? I mean, Nimbus has got one, and people have tried it before, but why do you think that never happened?
I think it's similar to the E1.L, right? It's a lot of capacity. I
Too
mean,
much.
the 3.5-inch device, you could have what, 3 or 4 layers of PCBs, tons of NAND, and you could. I think you mentioned Nimbus. I think they had like 100 TB SSD like a year ago. You could build even larger with today's SSDs. But do you really all want that all in one box? Kind of what you've seen in the hyperscale and even the OEM space. We don't want to put all of our eggs in one basket. We'd much rather have smaller devices and many of them because hardware fails. I mean, hardware will fail, will wear out. You have random failures, and you distribute your workload. You have, one controller and a smaller blast radius means more performance. You don't have to worry about NAND contention. You don't have to worry about crazy controllers that need to address, when I say like 4 layers of PCBs. I mean, unless you put a
Yeah.
controller on each of those and behind a switch. I mean, that's just complexity. We want simplicity. Simple, simple, simple. That's what we need. And three and
Well,
a half, that's way too much space.
too much. Okay. This is really interesting conversation. I think that when we looked at Ruler when it first came out, there was quite a bit of confusion because there were so many different shapes and sizes and messaging. You use this one for this, and this, and this, and it was just too much. And OEM, ODM support was poor. But now it feels like we're kind of teetering on adoption there. When do you think Ruler form factors outsell U.2?
My guess is probably 18 to 24 months from now. As you kind of indicated earlier, the hyperscale is going to drive that, right? So hyperscalers, as we start moving to E1.S, Facebook has contributed some of their designs. They publicly said they're going E1.S. Microsoft, we're moving E1.S. I can't speak for the other cloud providers, but from having other conversations, a lot of people are interested in that. And you're going to see maybe adoption is going to be a little bit slow, probably the first year. But then once people start shipping this, they've tested it, I think it's going to take off. And, we're probably by the end of 23 into 24 be my best guess of when it kind of crosses over. IDC had some projections. I put that in the article that I showed. I'm hopeful that we'll beat that we'll get kind of these E1.S, E1.L really overtaking U.2. But again, the market's going to speak. And I think as people have options or they show what you can do with E1.S, I think people are going to adopt it. So look at the Viking one, look at the Supermicro systems that they have. Samsung and Inspur have made some contributions about this as well. I think next year is going to be the big year. You're going to see a lot of introductions around E1.S. And that's going to shift the market when you can say, look, to your point with those small blades, can I get double the number of SSD slots in a blade? Who's going to say no? Hey, it's got great thermals. You can fit double the amount in a box. This seems like a no-brainer. E3 is not here today. So it's really an E1.S show for the general purpose market. E1.L is going to stay niche, right? I mean, you're not going to see everyone running out buying 32 terabyte SSDs tomorrow. But E1.S, you can get the gamut of 1 to 8 right now.
Well, yeah, I think it's cool. I think it's going to be really interesting to see how the big guys, Dell, Lenovo, HP, Cisco, whatever, Supermicro, all these guys, how they take this and in which direction do they run. And yeah, I hope you're right, because we like toys and we like new toys and different toys. So yeah, that would be good. And it feels like OCP and the summit that you were talking about, that the technology that's going there now feels more real in terms of what can be mainstreamed. Or in the early days, I mean, from Facebook, there was some cool stuff there. You guys had this, one of the first things I saw was this little M.2 sled guy that was like super novel for the time, but not broadly usable by the mainstream audience. This feels different. That some of the work that you guys are doing now, or maybe over the last couple of years, is really going into the mainstream and becoming in 2 or 3 years what you guys are doing in the hyperscale today, and it's maybe laying the groundwork and path for that.
That's a good observation. I mean, 8 years ago when I joined FacePrice, and 9 years ago, it was different. It was really a build a bare bones system. You look what Facebook did, what Google showed. I mean, it was bare bones. People weren't care. They didn't really care about how things looked, how it interacted. EMI, things like that.
Mm-hmm.
But as all the hyperscalers have started growing up and maturing as far as product offerings and the scale that we operate, you've seen us kind of pivot somewhere in the middle of where OEM was in this ultra radical bare bones sleds. We spent more time thinking about serviceability, ease of support, and then the market adoption, right? You don't want to be the only one buying a device. And I think the hyperscalers have all started figuring that out. Innovate where we need to, partner and kind of contribute with the rest of the industry where possible. So I think that's what you're seeing in OCP. You've seen these really radical designs that were hard to consume. So now it's this middle of the road where, hey, there's some really cool ideas. It's serviceable. It works well at scale, and it's not as hard to consume. It's not as radical. Plus there's a lot more software support. You have things like OpenBMC, things that are starting becoming more consumable. Hardware is really a brick without the software and the firmware on it. And I think that's kind of the other thing that you saw. We're starting to contribute firmware, and there's open source firmware, so now you can actually consume it. So I think this difference.
The summit's in November, is that right?
November this year.
Okay. So you'll commit to coming back and doing a pod a week or two after the summit. We'll talk about all the things that you've revealed there, including NVMe hard drive, and talk all the new tech and what's coming next.
Absolutely, happy to do that.
All right. Well, thanks for the time. I really appreciate it. This has been a great conversation, and we'll see if we get those rulers out there over the next year and a half.
We will. I think you'll get to see a lot of these at the summit. So anyone who's there in person will get to actually see them, not vaporware.
Yeah, another reason to go. Well, thanks for coming. Appreciate it, and look forward to another chat soon.
All right. Thanks, Brian.
Thanks all for tuning in. Bye-bye.